Replicating high fan-out registers has always been recommended for FPGAs because it allows the duplicate logic to move closer to destinations and shorten routing delays to improve timing. However, manual duplication is easier because synthesis tools tend to not choose good names for the duplicate components. Likewise, allowing synthesis tools to replicate until it is satisfied is not always as helpful as you might think. I have had many customers ask what maximum fan-out to set their synthesis tool to. In fact, the choice of setting a value, or maximum that is, depends on how far you are from meeting your timing objective and do you have sufficient resources left available. So keep in mind that if you have a high fan-out secondary control signal that you're making or generating, try and anticipate the fan-out and duplicate that logic at least once right from the beginning. And then, of course, be prepared to come back and duplicate it multiple times if necessary. When you duplicate logic, don't forget to also name the duplicate logic appropriately. Specifically, use the same name followed by an _A or _B. This will prevent the tools from seeing logic as being related, as in a bus, if it were numbered, say, _1 and 2. By default, synthesis tools tend to duplicate logic and give it a number, as in 1 or 2, and this forces the logic to be related and directs the implementation tools to keep it placed close together. So manually duplicate it and rename each duplicate _A, _B, _C, just as I described. The retiming option allows the tools to move registers forward or backward in a data path, and it is still recommended. The use of the IOB registers has always been to clock data in and clock data off chip as fast as possible. However, no one has ever really talked about if it has any impact on internal performance. Well, it can, but it will depend on a few things. First of all, if the pin assignments are placed properly, they should be near the destination or source logic. If not, then there will be some internal net delay. But depending on the size of the die, and that's important, and the destination, this internal routing delay can become large. So make sure that your pin assignments are good. You might even consider making some area constraints to keep the logic near those I/O pins. If you decide that your input registers don't need the IOB registers, then the tools can disable the IOB register placement. This will then allow a CLB register to be used, and the input time will have its delay increase as you might expect. So if you still need fast input-output times, you might want to stick with the IOB register. But in case you want to test this, to turn off the use of the IOB registers globally, disable it in the synthesis tool and then in the mapper as shown in the screenshot. Then if you need some registers placed into the IOB, say on critical paths, you can then use the UCF attribute directly in your UCF file. This will require you to know the instance name of those flip-flops, but with a little bit of effort you can detail control the actual use of the IOB flops. So let's review what we've learned in this module so far. First of all, synthesis tools can move synchronous resets from control ports to the data path. And this is one of the strongest reasons to design with synchronous sets and resets rather than asynchronous sets and resets. Likewise, the same kind of functionality is built with clock enables. Very powerful, very helpful. We also recommend you avoid the use of global resets, and the main reason here is because we have the GSR for setting and resetting every flip-flop in your design if you want. So don't design that in your code. Instead, instantiate the startup block in your design, and that'll save all that routing resources. Also, you should take advantage of the ability to initialize all your registers from your HDL. Okay? And if you can remove a global reset, you must keep in mind you're going to save a lot of routing and build a faster design. And that's because the implementation tools will now have lots of faster routing resources available that they can use at their discretion. You should also avoid resets if you want to infer your shift register LUT, because of course the shift register LUT does not actually have reset functionality. Other things we learned: Avoid asynchronous resets on block RAMs. The block RAM's output register only supports a synchronous reset. You should also avoid asynchronous resets on DSP slice resources because those flip-flops only support a synchronous reset. Keep in mind, ILB registers can make it more difficult to meet internal timing. Again, they help clocking in data and clocking data off chip. It's the fastest way to do that. But internal timing might, keyword might, suffer. It'll be up to you to decide if that's the case and to turn off the use of the ILB flip-flops on those critical paths. And we mentioned to you again that the way you're going to do this is to deactivate the automatic use of the ILB flip-flops and then manually map those specific flip-flops to the ILBs with a UCF attribute. Use ILB registers again only for improving I/O timing. And again, this will also depend upon if you have a very large FPGA where the die area is very large compared to, say, a smaller density device. Finally, Xilinx recommends not using the synthesis option to convert asynchronous resets to synchronous resets. Recall we mentioned this option as being a synthesis option, and it's a little deceitful because it doesn't really communicate in your HDL what you're trying to infer. And synthesis tools do work best when you code the HDL properly for what you want. Well, there are several very useful resources available to you on support.xilinx.com. The Synthesis and Simulation Design Guide discusses some of these same topics we have here. The XST User Guide is very helpful for example inferences of architecture resources, especially since we've talked a lot about the shift register, block RAM inference, the DSP slice inference. This is often what is most helpful to customers, so I'd strongly encourage you to check this document out. That's the Synthesis and Simulation Design Guide. Note that all the coding techniques that we've talked about here apply to XST. If you want coding styles and attributes for another vendor's synthesis tool, that's going to be up to you. You'll need to go to their website and learn more about their tool and what you need to do to code for it properly. If you want to learn more about the various synthesis options that are available in XST, I recommend you check the help menu from within XST. It's very helpful, but generally I still go with the defaults and only work with the options we recommend here and in the Designing for Performance course. To learn more about the startup block and other Xilinx primitives, we encourage you to check out the Xilinx Unified Libraries Guide. Very helpful to learn a bit more about the silicon as well, but the Libraries Guide is a nice intermediary between actual instantiation and the functionality that's actually defined by the silicon. Finally, thanks for listening to this recorded learning on Spartan-6 and Virtex-6 HDL coding styles and coding techniques, Part 2. Again, my name is Frank Nelson. Thank you very much for your time and attention, and thank you for your business.